In this video, we're going to take a look at standard D6, which is going to explain about angled projectiles. When a projectile is launched at an angle above the horizontal, so not a horizontal projectile, but at some angle, the velocity that it's going to have initially is going to be both in the vertical and the horizontal directions. So we can't treat this like the horizontal projectile where we had zero initial velocity vertically. In this scenario, the velocity that we launch it with, we're going to have to break it into its vertical and horizontal components and try to figure out how this object's going to move. So when we're looking at this, the acceleration in the vertical direction is going to be a negative 9.81 meters per second squared. Vertically, however, the velocity at the peak is going to be 0 meters per second. So even as it's arcing through the air, when it hits that very top point, the vertical velocity will be 0. And the horizontal velocity will be constant. So whatever horizontal velocity or component of velocity that's horizontal when you launch it, that will stay constant throughout its whole flight. The motion upward to the peak of the trajectory, it has a symmetry to the downward peak. So the motion up and the motion down both have symmetrical aspects. The things that are symmetrical are the initial vertical velocity that it's launched with is the same vertical velocity that it hits the ground with, just in the opposite direction. So you launch it up with the vertical velocity, and when it gets back to that same level, it's going to be heading down with the vertical velocity that's exactly the same, just in an opposite direction. When we talk about the time it takes it to get to the peak is exactly the same time as it takes it to get from the peak down. And these two aspects we can use to understand how to work about an angled projectile. So we're going to work about the peak, and we'll always just find the time up to the peak or the time down from the peak, and we can use that or double it to determine what the total time is. When we talk about the factors that are going to affect the trajectory of a projectile, there's two that are important. The angle it has to the horizon, right? So how much angle it has to the horizontal, and whatever initial velocity we have. Because acceleration due to gravity is going to be constant, the mass of the object doesn't matter. It just matters what angle you're throwing it at and what velocity it's leaving, being launched with. When we talk about projectiles, angled projectiles, the one thing that we really have to get a handle for is what angles or what key aspects do we need to understand about getting objects when they're launched, either to go the furthest distance or spend the most time in the air or go to the greatest height. So we call these maximums. If you're trying to get the most horizontal distance out of a projectile, 45 degrees will always give the greatest horizontal distance. So if you're trying to throw something as far as you can, you want it to leave your hand at 45 degrees. It will take the greatest length of path. If you want the object to go higher in the air, so your projectile gets the greatest height, the greater your angle, the higher the object will go. So 90 degrees would be the greatest. If you want the object to stay in the air the longest, the greater the launch angle, the more time it's going to be in the air. So as you affect your launch angle, as your launch angle increases to 90, so does your height and so does your time in the air. But it increases, it's at its maximum at 45, so that means that anything above or below 45 degrees of launch angle will give a lessened horizontal distance. If you're trying to compare two different horizontal distances, the horizontal distances will be the same for any two angles that add up to 90 degrees. So that means a 30 degree and a 60 degree launched object will land in the same spot. The differences will be how long it takes them to get there and the angle in which they land. So if your 30 degree will be a less time in the air because it has a smaller launch angle, but it'll come in at a little bit more of a flat angle. Whereas the 70 degree or 60 degree will go up and be in the air much longer, but when it comes into the ground, it will hit at a much more vertical aspect. One of the things that we have to be able to do with angled projectiles, besides being able to identify how the changes to angle affect the trajectory, is we have to be able to take a look at some projectile that's launched at an angle to the horizontal and be able to figure out what the vertical and the horizontal components are. So let's do an example of this. In this example, the ball is launched at 4.5 meters per second, and it's making an angle with the horizontal of 66 degrees. What we want to do is find the vertical and horizontal components of that initial velocity. So what we're going to do is we're going to make this basically into a right triangle. And here you can see that we have the 4.5 meters per second, on the hypotenuse of our right triangle, and that the angle of 66 degrees is making an angle with the horizontal. The two blue legs of the triangle are both vectors. The one that is horizontal is our velocity vector that's horizontal. And the one that's vertical is our vertical velocity vector. So from our 4.5 meters per second, that's at an angle of 66 degrees, we can break that initial velocity into two components, a vertical one and a horizontal one, that represent this motion. It's equivalent to this motion, but even though it's representing it, the two would be the same. So if you have two, horizontal and vertical, they mean the same thing as the 4.5. So let's go through the process of determining at 4.5 meters per second at 66 degrees what the vertical component of that velocity is. We're going to use our trig function, and we're going to use the sine function, because sine theta is going to be equal to the opposite of the angle divided by the hypotenuse. So our angle is 66 degrees right here. Our vertical velocity is opposite that angle. So sine theta opposite divided by hypotenuse, that means the sine of 66 is equal to the magnitude of our vertical component, that's the velocity of the y, divided by the magnitude of our hypotenuse, that's 4.5 meters per second. And if we take sine of 66 and multiply it by 4.5 meters per second, you get a velocity in the vertical direction of 4.1 meters per second. Now, if we do the same thing for the horizontal velocity, this time we're going to use cosine. So cosine theta is adjacent divided by hypotenuse, and our adjacent side is going to be our velocity in the x direction, and our hypotenuse is 4.5 meters per second. So if we take cosine of 66 and multiply it by 4.5 meters per second, we're going to get a velocity in the horizontal direction of 1.8 meters per second. And these two, velocity vertical 4.1 meters per second and velocity horizontal 1.8 meters per second, represent the components of this 4.5. The two taken together, if you're moving 4.1 meters per second vertically and 1.8 meters per second horizontally, so if an object has those two velocities, both vertical and horizontally, it's the same thing as moving 4.5 meters per second at an angle of 66 degrees.